Okay, so today I wanted to talk about matrices and vectors in linear algebra. And the reason for that is because we're going to start talking about linear systems of differential equations. And that's differential equations that can be written as matrix vector products, or we have a whole bunch of different equations that are interconnected. And in some cases, you can write that down as a matrix vector equation. And so we want to be able to solve those types of equations as well. But before we get into that, we need to know a little bit about matrices and vectors and some linear algebra. So hopefully you've seen some of this stuff before. If not, there's only a few different things we need to know about. Okay, and so we'll kind of cover those things, but you should also watch the recorded video lectures, and there are plenty of materials online in order to kind of pick up these ideas. So I'm going to kind of keep this brief and just introduce kind of some of the big ideas that we need in order to solve linear systems of differential equations. Okay, so first off, what is a vector? What is a matrix? So a vector is just, we're going to kind of think about it just as a list of values or of equations. You can have variables in here as well, numbers. You can, something like this would be a vector, and a, b, and c could just be numbers. They could be functions if you're having like a vector function, or they could be like having variables in them. And a matrix is going to be a 2D version of that. So there's kind of a 2D array of numbers. All right, and we're going to work with these two different ideas, matrices and vectors. Okay, so there's a vector and it's a matrix. So one thing you could do right away is we want to be able to add and subtract them. As long as two matrices or two vectors are the same size, you can add and subtract them. And that's just done element wise. So for example, if you had like AB plus CD, that would give you another vector that's A plus C, B plus D. Okay, and you can do that not only for vectors, but matrices, just each element you add with the corresponding element. And if two things are different sizes, so you can't do addition or subtraction. So for example, these two things right here, you couldn't add or subtract them because they're not the same size. Okay, we can also multiply by a scalar value. So a scalar value is just what we're used to. So like, for example, some constant C would be a scalar, a variable X would be a scalar. And you can multiply vectors and matrices by scalars. So for example, if we had something like C times the vector AB, each entry gets multiplied by the scalar. So this would be C times A, C times B in a vector form. Okay, so just again, pretty simple. Whatever the scalar we're multiplying, you just multiply each entry by that scalar to get your result. And it's going to be the same shape as what we started with. Okay, here's where it gets a little different. Okay, so that's pretty much normal how we think about addition and multiplication. But if we want to multiply matrix and vectors together, they need to have right shape. So for example, we can multiply a matrix A, B, C, D by a vector E times EF. And how we do matrix vector multiplication is we take the row of the first of the matrix times the column of the vector. Okay, so this would be A times E, and we add the separate entries. So it'd be A times E plus B times F. This is going to result in a vector that's A, E plus B, F. And then for the second entry, we're going to have C, E plus D, F. C, E plus D, F. Okay, so first off, maybe I should backtrack a little bit. When we're talking about matrices and vectors, they have a certain shape that we associate with them. So for example, in this vector, it has 3 rows and 1 column. So we'd call that a 3x1 vector or matrix. This is a 2x, it's got 2 rows and 2 columns, so it's a 2x2 matrix. We can only multiply things that are of the right shape. So we only need to multiply things that are m by n. You can only multiply that by things that are n by something else, and by k. So this inner here, n and n, have to be the same. If those are the same length, then you can multiply two matrices together. So in this case, the number of columns in the first product has to be equal to the number of columns in the second term. And if that's true, then you can multiply them together. And so the resulting shape is going to be m by k. So in this case, it was a 2 by 2 multiplied by a 2 by 1. So the resulting is going to be a 2 by 1 vector. And each entry we find by taking the column, or the row times the column, all right, and adding the entries together. All right, so that's how you do matrix vector multiplication. So you could do, like we said, matrix vector. You could do a matrix matrix. So, if you had a 2 by 2 times a 2 by 2, you'd end up with a 2 by 2. All right, we'll see that a little bit more later. Then we can take transposes of matrices. So the transpose of a matrix, if A is a matrix, we write the transpose as A with a T superscript. If we have A, B, C, D, we take the transpose of that. Basically, that just rotates it around its main diagonal. Okay, so we leave the diagonal the same. So A is going to stay the same, but this B is going to flip over to here. The C is going to flip back, and the D is on the diagonal stays the same. So that's the transpose. We just flip all the entries, rotate them around that middle diagonal, leaving the diagonal alone. So that's the transpose of a matrix. All right. So that's kind of some basics. Some things that we're going to need to do in order to solve linear systems or differential equations is we're going to need to determine whether or not a matrix is singular or non-singular. We're going to be able to do determinants. So the determinant of a matrix is written like this. So we have the determinant of A is written like this with absolute values signs. If the determinant equals 0, we call that singular. Or sometimes we also write it as DET, the determinant of A. Does not equal 0, then it's non-singular. Okay. If it's non-singular, a lot of nice things happen. We can find like a matrix inverse. So a matrix inverse means that when we do A matrix multiplied with the inverse, we get the identity matrix. And the identity matrix is just a matrix with ones on the diagonal and zeros everywhere else. Okay, or it doesn't matter. You can also multiply A inverse A. Should also give you the identity. So that's what a matrix inverse means. Okay, and you can't always find this. So if a matrix is singular, A inverse doesn't exist. We can't find a matrix like that has this property. But if it's non-singular, we can find the inverse. Okay, so first off, this problem is asking us determine whether the matrix is singular or non-singular. Okay, so that basically means we need to take the determinant and see is the determinant equal to 0 or does it not equal 0? All right, so how do we do the determinant? The determinant of a matrix, so we want to find the determinant of 4, 8, negative 3, 5. The determinant of a 2 by 2 is just the main diagonal subtract the opposite diagonal. So it's going to be 4 times 5 minus negative 3 times 8. Okay, it's 20 plus 24 is 44. So that doesn't equal 0, so that means that this matrix is non-singular. Okay, so that's a pretty simple rule for the 2 by 2. How would you find the determinant of a bigger matrix? Well, there's a couple different ways. So let me first talk about the general way. So in general, you have a bigger matrix. If you want to find the matrix of something like A, B, C, D, E, F, G, H, I, what we do is we go along a row or a column and we multiply by a matrix, a determinant of a submatrix. So for example, one possibility would be, this would be like A times the determinant of the submatrix. Okay, and so the submatrix means we take out this row and this column, and we do the determinant of the remaining matrix. We would do the determinant of EF H times I. Okay, and we know how to do the determinant of this. It's EI minus HF. And then if you're going along the top row, it would be minus B times the determinant of the submatrix. So the submatrix, we do that column out, that row would be the determinant of D F G times I plus C times the determinant of the submatrix D E G H. Okay, taking out this column and this row. All right. And you alternate. So you go along any row or any column, you take that entry times the determinant of the submatrix, and then you go minus the next one, plus, minus, and so on. Okay, and you could do this many different ways. So you could have gone down this first column or the second column, third column, you know. So in general, if you had a matrix with a bunch of zeros in it, you could pick a row or column that has a lot of zeros in it so that a lot of these terms just disappear. And then you do the determinant of the submatrix with the same rule. Okay, so in this case, the submatrices are 2 by 2, and we use this little formula. If they were 3 by 3, you'd have to apply the rule again. Okay, so it's kind of a recursive definition. The other way to do determinants of 3 by 3s only, let me just share this little trick, is with diagonals. So if I have a matrix A times B, C, D, E, F, G, H times I, we think about all the diagonals going from left to right. So we have like a diagonal here, and then when you hit the edge, it goes off, comes back to G. And we can think about this diagonal here, C, going to D and then H. So we got 3 diagonals in this direction. In that, we multiply all those together and add them, and then you subtract the ones going the other way, the reverse diagonals. So this determinant is also equal to A times E times I plus B F G plus C D H, but then we subtract the other ones. So minus C E G minus B D I and minus A F H. Okay, so that's a way to do this. Only works for 3 by 3s. You can do this diagonal trick. Okay, add the ones going left to right, subtract the ones going right to left. And that's if you were to add all this out and simplify, you'd see these two are the same. They're 3 by 3. Okay, so that's kind of a little bit easy. Sometimes that's a nice trick for 3 by 3s. Anything bigger in practice, you should just use a computer. Okay, it's worth knowing this definition, but doing it out by hand is a huge pain, and the computers can do it instantly. So just plug it into your computer, or graphing calculators can do this as well. Okay, so just use that tool. Don't necessarily work this out. Okay, so let's answer this question here. We had this matrix. We found its determinant is non-zero, so that means it's non-singular. And since it's non-singular, it has this inverse matrix. So how do we find the matrix inverse? The matrix inverse is found there's a few different ways to find it. In general, using a computer is fine, but for 2 by 2s, it's worth knowing. The inverse in this case is going to be 1 over the determinant, and then what we do is we modify this matrix here. So it's going to be What we do is we flip this main diagonal. It's going to be 5 times 4. And then we negate the backwards diagonal. So it's going to be 3 minus 8. Okay. So the determinant we just already said is 1 over 44, or is 44. So this will be 1 over 44 times 5 minus 8, 3, 4. Okay, so that would be the inverse of this matrix right here. Okay. So in 2 by 2s, what happens is you just flip the main diagonal. So the 5 and the 4 flip, and then you take the negation, you flip the sign on the other diagonal. Okay, and you can do that for higher order, for 3 by 3s and such. But in practice, I would just use a calculator for that. Okay, so that's how you find the inverse of 2 by 2s. All right. The other thing that we need to know to solve linear systems, and this is the really important part, is we need to find eigenvalues and eigenvectors of a matrix, of square matrices. So what does it mean, eigenvalue, eigenvector? So if we have a matrix A, we can multiply vectors to A. For example, I can multiply A by a vector B. Right, a little arrow here to show that's a vector. For special vectors V, I might get out a multiple of that vector, lambda V. Okay. So if I just take this matrix and I multiply by a random vector, I'm going to get another vector out, but it's probably going to not be just a multiple of that vector. So for certain vectors, this matrix A just scales it by some value lambda. We multiply A by some special vectors, that turns into just the scaling of that vector. Okay, so for example, if I just multiply this by 1, 1, 1, I'm going to get something else that's probably not just a multiple of 1, 1, 1. Okay, but for a special vector, I'll get just a multiple out of that vector. And so the question is, these special vectors are called eigenvectors, and the scaling value is called the eigenvalue. Okay, so V is the eigenvector, and lambda is the eigenvalue. Okay, and so these tell you a lot about a matrix. Okay, so it's an important thing to know when you're looking at a matrix. What are the eigenvalues? What are the eigenvectors? So for a 3 by 3 matrix, there should be three eigenvalues and 3 sets of eigenvectors. Okay, so how do we find this? So what happens is, so if you look at this equation right here, we can kind of do a little bit of manipulation. So I can say A times V, and if I subtract the lambda V across, that means I get the 0 vector. All right, and then this lambda you can kind of think as lambda times the identity, and that allows us to factor out the vector V. So we can see that this is also the same thing as saying this new matrix here, A minus lambda I, which just looks like our matrix, but we subtract lambda along the diagonal, times some vector gives us the 0 vector. So in general, if you just pick a random lambda, then when we're thinking about this equation, we know something about this when there's a 0 on the right-hand side. Okay. Unless this matrix here is special, is singular, in fact, the only V that works is the 0 vector. Okay, so like in general, if we take a matrix times the 0 vector, we're going to get 0 out. Okay. And there's only singular matrices we can multiply by something non-zero and get 0 out. Okay. So if this A minus lambda I is non-singular, no vector V that we put in except for the 0 vector is going to give us 0 out. So what does this tell us? It tells us that this matrix A minus lambda I needs to be singular. It tells us that the determinant of A minus lambda I needs to be 0 in order to get good answers to this equation. Okay, so this is how we figure out what lambda is. This is an equation that we can try and solve. Okay, the determinant of a matrix is just is just a scalar value. Okay, so we can try and solve this equation right here for lambda. So what does that look like? Basically, we have the determinant of this matrix. Subtract lambda from all the diagonals. And find the determinant of that matrix. Okay, so let me use my little 3x3 trick to find the determinant of this matrix. So it's going to be along these right diagonals, we have 5 minus lambda times minus 5 minus lambda times minus lambda plus -1, 9 times 5. So that's 9 times 5 is 45, minus 45, plus, and then we have a 0, 0, so that's going to be 0. And then we go to the reverse ones, minus, so that goes to 0, -1, 0, lambda, that goes to 0. So we just have minus 5 minus lambda, 9, -1. 9, -1. All right, so that's a polynomial. Let's kind of try and simplify this a little bit. So we have 5 minus lambda, -5 minus lambda. Put the negative off at lambda, minus 45. The -1 and the negative are going to cancel, so we have plus 9 times 5 minus lambda. So in order, we want to find the lambda that makes this equal to 0. Okay, that's what our equation wants. Determinant of this should be 0. So that means this polynomial, we want to find when is this polynomial 0? What lambda makes this equal to 0? Okay. So if we were to factor this all out, it's going to be a cubic in terms of lambda. Okay, so that's the kind of the key thing here. So it's a polynomial, so it's basically going to come down to factoring or doing something like that. All right, so just thinking about how to solve this for lambda, it looks a little tricky. So at first, I kind of want to try and factor out this 5 minus lambda because we have a 5 minus lambda here. But this term here, this 45, doesn't have a 5 minus lambda. So let's try and distribute these things out and see what we get. So I've got, let's kind of in the sense we've got this minus is going to be plus 5 plus lambda times lambda. So we have 5 lambda plus lambda squared times 5 minus lambda minus 45 plus 45 minus 9 lambda. Okay, so that's a good sign. So this 45 and minus 45 cancel, and then let's try and we solve this in minus 9 lambda. We want to bring that in, so let's distribute this one more time. We have 5 lambda times 5 is 25 lambda. We have 5 lambda times minus lambda, minus 5 lambda squared. And then we have lambda squared times 5 is going to be plus 5 lambda squared. And then we have minus lambda squared times lambda, minus lambda cubed, minus 9 lambda. All right, so the plus 5 lambda squared, the minus 5 lambda squared cancel. We're left with minus lambda cubed and then we have minus 9 plus 25. It's going to be plus 16 lambda equals 0. All right, so factoring this 1 lambda out, we find, in fact, let's factor negative lambda out. So we have lambda squared plus 16, 0. So either lambda, one answer is lambda equals 0. Okay, so one eigenvalue is 0. And then and you find when is lambda squared plus 16 equals 0. You can bring the 16 across, so minus 16, take the square root. We're going to get imaginary, so we're going to get 4i plus or minus lambda. So one eigenvalue is 0. The other two eigenvalues are plus or minus 4i. Okay. And just as before, we're going to get these pairs of complex values. Okay, so before we were dealing with characteristic polynomials, it's very similar. We're going to get pairs of complex eigenvalues. Okay, so that's the eigenvalues, 0 and plus or minus 4i. There's 3 of them. It's a 3 by 3 matrix. That's what we would expect. Okay, so that's the first step, finding the eigenvalues. How do we find the eigenvectors? So eigenvectors, basically, now that we know lambda, so if lambda equals 0, means that we need to solve A times the vector V equals lambda times V. So now that we know lambda, we can plug that in. So in this case, the 0, we just have a 0 vector, and we need to solve this system of equations for V. We've got a matrix. We've got 5 minus 1, 0. 0 minus 5, 9. 5 minus 1, 0 times a vector v1, v2, v3, we divided it as, equals zeros. Okay, we want to solve this system for v1, v2, v3. Okay. To find the eigenvector that goes with 0. All right, so how do you do that? So there's lots of ways you can do that. I mean, computer obviously works. There's something called row reduction that works. Probably the most obvious way to do this is just to write it as, this is really 3 equations, right? If we think about matrix times vector multiplication, this is 5v1 minus v2 plus 0v3 equals 0. So if you write this out as an equation, 5v1 minus v2 equals 0. And then you have the second equation is the second row times the column. So 0v1 minus 5v2 plus 9v3 equals 0. And then the last one says 5v1 minus v2 equals 0. Okay, so you've got 3 equations and 3 unknowns. We want to try and solve for v1, v2, and v3. So how do we do that? So we kind of just want to go one step at a time. So for example, this first one, we can rewrite as 5v1 equals v2. All right. 5v1 equals v2. We can plug that in to here to solve for v3. So we have negative 5 v2s really times 5 v1 plus 9 v3 equals 0. So you get negative 25 v1 equals negative 9 v3. Divide that across, we get negative 25 over 9, negative 9, so plus v1 equals v3. All right, so we know v3 and v2 in terms of v1. And so what you see is if we were to do this again, so say we plugged in, we have 5v1 minus v2 is 5v1 minus 5v1. So here we get 0 equals 0. All right, so that's a little tricky because now we're kind of stumped. We're like, well, how do we go solve these equations? And what's key here is that when we're talking about eigenvectors, there's not just one eigenvector. There's a whole family of eigenvectors, which means that when we're solving this system of equations, at some point we'll have to make at least one choice in order to figure out what v1, v2, and v3 should be. So there's like one free variable, is what we call them. In this case, the free variable could be v1. So for example, if I pick v1 equals 1, then I plug that in. I have 5 times 1 equals v2. So that means v2 equals 5. And if v1 is 1, then 25 ninths times 1 is v3. So v3 is 25 over 9. So the vector 1, 5, 25 over 9 is an eigenvector. Okay, but we could have picked anything for v1, and that would still be an eigenvector. And that's just going to scale the eigenvector. So if I pick 2, all these would be twice as big, but still, it would still be an eigenvector. Okay, we plugged in any multiple of this into this equation right here, we would get the 0 vector out. Okay, so that's how we solve eigenvector equations. So you pick the eigenvalue that you want to solve for, and then just solve that equation, solve that system of equations. And at some point at the end, you're gonna run out of equations, and you're gonna have to make a choice. So basically, you want to get all of the variables in terms of one of the other variables. We got v2 and v3 in terms of v1, and that allowed us to pick v1 and find the rest. So let's try again. So what if we had lambda equals, now we want to do the 4i. If this didn't happen, if you had uniquely determined all v1, v2, v3, you would know that you made a mistake sometime. Okay, we're going to have to make a choice for sure. And so if you end up not having to choose a value for one of the variables, then you know that you've made a mistake somewhere. So let's think about 4i. So again, we want to think about this. So we have a times a vector v equals 4i times that vector. In general, now that we don't have this 0, we want to actually rewrite it as like a minus 4i times lambda times a vector v equals 0. Okay, it's nice to have the 0 vector over here. So we can write this as 5 minus 4i, negative 1, 0, 0, negative 5 minus 4i, 9, 5, negative 1, minus 4i times v1, v2, v3 is going to equal all zeros. And we want to solve this system of equations for these v's to find the eigenvector that goes with 4i. Okay. So let's write these equations out again. So we have 5 minus 4 times I v1 minus v2 equals 0. We have 5 minus negative 5 minus 4i v2 plus 9 v3 equals 0. And then we have 5 v1 minus v2 minus 4i v3 equals 0. Okay. So in this case, we can see a couple things. So let's add this across. So we have v2 equals 5 minus 4 times I v1. All right, so let's plug that in everywhere. So we have negative 5 minus 4i times v2, which is 5 minus 4i v1 plus 9v3 equals 0. And then we have 5v1 minus v2, so that's minus this, minus 5 minus 4i v1 minus 4i v3 equals 0. All right, so now that we try and simplify these equations. So we have minus 5 times 5 is minus 25. Minus 5 times minus 4i is plus 20i. And then we have minus 4i times 5 is going to be minus 20i. And then we have minus 4i times minus 4i is going to be plus 16i squared v1 plus 9v3 equals 0. All right, so these i's, 20 i's cancel. I squared, I is the square root of -1, so I squared is going to be -1. So we have negative 25 minus 16. So that'll be negative 41 v1 plus 9 v3 equals 0, or 41 v1 equals 9 v3. All right, so that's that equation. Let's look at the last one. We have 5v1 minus 5v1, that cancels. And then we have minus, so we have 4i plus 4i v1 minus 4i v3 equals 0. So something interesting happened. I think I made a mistake somewhere. So we see here that this is 4i v1 equals 4i v3. And if you cancel those out, the 4i's, we see that v1 should be equal to v3. Okay, but that's clearly it shouldn't work because of this equation right here. It says 41 v1 should equal 9 v3. Okay. So what went wrong here? Just double check our equations. Well, so in fact, I guess there is one way that this could be true. Okay, that is if v1 and v3 are both equal to 0. So v1 is equal to 0. Okay, but that doesn't work. So if that's the case, so v1 equals 0, then that means v3 equals 0. But then if v1 is 0, that means that v2 is also 0. So all are zeros, and that's not what we want. Okay, we don't want all 0 vectors, all 0 vector. We should be able to make a choice somewhere along the line. Write down the matrix, right? So well, I wonder if I did something messed up here. So this should, so we got minus 5 times minus 5, minus 5 times 5 is negative 25. And then we have plus 20i minus 20i. So that should always happen canceling. And then we have minus 4i minus 4. So negative times negative is positive. And the I squared makes it negative again. Okay, so I think something happened here which made this should have made this instead of minus 41, it should have been minus 9. Okay, and so we get minus 9b1. We get 9b1 equals 9b3. Okay, and that turns out to be the same here. Okay, so v1 equals v3. Okay, so that means we can pick v1 or v3, and then that's going to determine what v2 is. So for example, if I pick v1, we want to pick something so that they're not all 0. If I pick v1 to be 1, then the eigenvector will be 1. Plug that in up here for v2 is 5 minus 4i. And then v3 is equal to v1, so it equals 1. So the eigenvector looks like this. 1, 5 minus 4i, 1. And in fact, when we're doing these complex eigenvalues, it turns out that if we wanted to do the one for lambda equals negative 4i, we could do that all again, but it turns out that the eigenvector is just a complex conjugate. So instead of 5 minus 4i, it's going to be 5 plus 4i. 1, 1. So that's the eigenvector for the minus 4i eigenvalue. Okay, so when we have complex eigenvalues, we only have to find the one eigenvector, and then we already know what the other eigenvector for the other eigenvalue is. Okay, so that's pretty much eigenvalues. So eigenvalues, let me just kind of review that. In order to find the eigenvalues, we want to figure out what lambda makes the determinant of a minus lambda I equals 0. Okay, solve that polynomial for lambda. And then once you have that, you want to solve this equation for v for each lambda that you have. And if you have a complex lambda, you just need to pick one, find the eigenvector, and you can take the complex conjugate in order to figure out what the eigenvector for the other complex eigenvalue is. So basically, well, once we get into linear systems, we're going to start writing our differential equations as x, like a vector, derivative equals a matrix times x. Okay, and we can solve this differential equation here. This is a system of differential equations by looking at the eigenvalues and eigenvectors of A. All right, and so we'll get more into that next week. And so we're going to need to do this eigenvalue, eigenvector thing quite often about the matrix A in order to figure out what the solutions to this system of differential equations is. Okay, so we'll get into that more later. So until then, I'll see you guys next week.